what I'm really going to talk about this morning is a new way of addressing what may well be the biggest bottleneck in quantum networks. Namely, how do you measure and tune individual quantum devices? And you'll see as I go on that that's hard enough even for an individual quantum device, depending on the particular platform you're using. It's going to become a vast problem when you extend to 200 or 5 million quantum devices for eventual applications and scalable technologies. And fortunately, machine learning is rapidly becoming available. I think it's the fastest moving part of computer science at the moment. And the techniques are coming ahead so fast that they're going to be available to meet this challenge that we're going to have in quantum networks of how do we measure and tune devices. And we've been doing this for about 3 years now in the lab in Oxford, and I can tell you in summary what I've learned in that time. And it is that machine learning is simultaneously completely universal and applicable to any problem, because the emphasis is on the machine learning. So you're not programming the machine to do a task, you're programming the machine to learn how to do a task. And once it learns, it can get better and better at it itself. So that is true on the one hand. Simultaneously, machine learning needs to be very carefully tailored and trained for a particular task that you want it to undertake. And so we're now using we're about to extend to 4 different methods of machine learning that we use in the lab, and I'll touch on those as I go along. And in a sense, you can think, actually, this is a bit like the stuff between our ears, isn't it? That we have between our ears this amazing learning machine that can learn to do almost anything at all. And if you watch a kid, to a large extent, it learns by itself. So it's hugely flexible, hugely universal, and yet education matters. And so we invest huge amounts of time, you know, the case of the people in this room probably mainly in universities, but at every stage in life as parents and teachers and so on, in educating and training other humans to be able to use this universal learning machine for particular tasks to which they want to apply it. So we'll find that that's true with the machine learning too. So here we are. The particular implementations I'm going to talk to you about work at cryogenic temperatures, and there's Natalia Ares, who leads this work in Oxford, and we're standing in front of a cryostat, which rather unusually has got the covers off, so usually it's got grey covers on, which means you can't see the beautiful shiny gold surfaces inside that take you down to a temperature that's colder than anywhere in the universe that we know of outside a human laboratory, so routinely about 20 millikelvin. And the particular implementations that I'm going to talk about this morning are spin qubits in 2 forms, really. One is a sort of simple spin qubit, where a 0 is up and a 1 is spin down, and we use superposition states for qubits. And then and those are implemented in a single quantum dot in our lab. And then singlet triplet qubits, where the information is encoded in whether the 2 spins together make a singlet or a triplet, and those offer some advantages in robustness. And so for each of those, you want quantum dots in a band gap engineered structure. Can be group 4, or these ones are group 3, 5, and they're defined by surface gates. And herein lies the challenge, that if it's a single dot device, you're working basically in a sort of 5-dimensional space of the voltages you're trying to tune up. If it's a double dot device, you move into an 8-dimensional space, and that's just for 1 qubit. Of course, 1 qubit by itself doesn't do you much good, so the more qubits you have, the more dimensional space you're moving into. And just to get you enthusiastic from the start, if you've got a single dot device, a good human, might do it in a day or so. If they're experienced, maybe less than a day. Might take a bit longer than that. The machine can now do it in 4 minutes. And if it's a double dot device, most people take days or weeks to tune up a double dot device. The strongest claim I've ever heard is from Charlie Marcus, who thinks he can do it in 2 hours. I don't know how big a team he needs with us to be able to do it in 2 hours. And in our case lab, the machine is already routinely doing it in 1.5 hours. And one of the graduate students who works on this, Dominic Lennon, says it's as if all your life you've been washing your shirts in the bathtub with a bar of soap. And it's quite time-consuming, and you don't enjoy it very much, but you've got to get your shirts clean, and it's the only way to do it, so you cheerfully do it every week, you see. Until you acquire a washing machine. And you find that all you have to do is put your shirts in the machine, put in some detergent, shut the door, press the start button, come back 2 hours later, and your shirts are washed. It's fantastic. And you never again want to, hi, Yo, come on in. You never again want to go back to washing them with a bar of soap by hand in the bathtub. And now, basically, nobody in our lab tunes up any of these devices by hand. They use the machine for all of them. So what are we trying to do? Well, here are the 2 cases for the single qubit, single spin case. We're basically trying to have a single quantum dot in which we can have an odd number of electrons, preferably just 1, so that it can be spin up or spin down. And the way to view that is with these stability diagrams, which in the case of a single dot device are often plotted as a bias voltage, source drain voltage as the vertical axis, the gate voltage as the horizontal axis, and then either the current in this case or the differential conductance sometimes plotted as the grayscale or the color scale. And when you do that, you've got a good device, you get these characteristic diamonds. They're called Coulomb diamonds, and they're the regions in which there's not enough energy to put 1 more electron onto the dot or to take 1 electron off the dot. For the singlet triplet devices, you're rather trying to get 2 dots, each of them with 1 electron, and also with the sort of right size of tunneling barriers between them. And a signature that you've got there is also plotted in a stability diagram, but now often plotted as a function of 2 gate voltages. They're called the 2 plunger gates, which essentially control the energy of each of the quantum dots. And the characteristic that you've got a good double dot system that's going to be suitable for singlet triplet qubits is these pairs of triangles here in that kind of stability diagram. But you might look at this one here, because this shows you what the tuning problem is. Okay, you've got a region to the bottom left where no current flows at all, and you've got a region to the top right where current flows more or less whatever you do. And you're trying to find this region here, can't quite reach, but just here, where you've got the interesting things happening. Now, because of the way that PowerPoint works, we can only display 2-dimensional graphs. That's all we can visualize, okay? So as humans, we're used to displaying these things on a 2D screen. But please remember that they're really multidimensional. So in the case of a double dot device, this is part of an 8-dimensional plot. So there's now, I'm illustrating them for single spin devices and for singlet triplet devices, But of course, there's now a vast range of implementations that can be used for quantum computing. Amazingly enough, it's still true what we said at the start of the QIP-IRC in the UK in 2002, that it's too early to say which implementation will end up being used, or more likely which combination of implementations will end up being used. I think, nevertheless, it's true that whichever implementation you're talking about, tuning up is a challenge. It's certainly a challenge for the superconducting qubit devices. And colleagues in Oxford who work on the ion traps say, well, you know, to get an ion trap working, basically working, you don't have to do much tuning. But to get it working to the high fidelities that are going to be necessary for scalable quantum networks, tuning is certainly a challenge. So we've got the quantum revolution with this challenge of measuring and tuning qubits, but fortunately alongside it, we have the AI revolution, which is almost every week that passes producing advances in the ways that machines can learn how to do more and more complex tasks. And so that's why, although the general field is called artificial intelligence, the emphasis is on the machine learning. And one of the things that you'll see as we go through, the emphasis which has been on AI for classification is still important. We're not abandoning that, but the direction of travel is towards AI for decision-making. So we can think of these as decision-making machines. One of the fastest-moving companies in the UK is a company called Prowler.io, and its tagline is that it's about making decisions in complex problems. And I'm going to divide the results into sort of two sections. The first is what we originally set out to do, which is machine learning for measuring quantum devices. And then the second is what we then discovered we could do, which is machine learning for tuning devices. In 2016, I set the vision for the lab that within 5 years, the machine would be deciding what to measure next to the standard of a second-year graduate student within 5 years. And the graduate students said, well, if the machine's going to take over, what about us? What do we do? To which the answer was, quick, get your PhD before the machines are better at it than you are. Well, in fact, in terms of the goal of deciding what to measure next, it didn't take 5 years. It took 1.5 years. And on Christmas Eve 2017, the machine was taking decisions about what to measure next in ways that I'll show you. So let's first of all think about device measurements. And the key to this is the sort of what's now become classic machine learning, sometimes known as deep neural networks. And what you've got is you've got a high-level representation in a many-parameter space that by a series of mathematical transformations through a series of layers, that's why it's called deep neural networks, you transform into a lower parameter space that can do simple classification. And then, crucially, it can go back up again to reconstruct what you originally had. So the high-level representation might be all the pixels on that picture. The bottom one might be a cat or not a cat, but then we can go back up again. So this is the kind of way that it works. You take your high-level representation, which might be a picture, and then you have an encoder, which it encodes it. I've just shown 2 levels. It's usually a series of levels where you can do your classification. But then having done your classification, because of the probabilities of the connections that you've implemented, you can go back up through the decoder and reconstruct the picture of the cat. And this is now completely established in the world. for human-level recognition. Hands up anybody who's ever used an electronic passport control for immigration into a country. Okay, so the machine is now faster and more reliable than a human immigration officer at comparing the picture on the passport with the person in front of them. And it's not hard to see why. The machines, before they were implemented at Heathrow, were trained on 50 million faces to do the recognition with a sufficient accuracy and reliability to be used for making decisions about people's lives, whether or not they'd be allowed into the country. If you take a human immigration officer who looks at one face per minute for 40 hours in a working week, for 40 years of a working life, he'll, roughly speaking, have experienced by the end of his career about 4 million faces. So you can see why the machine has a big advantage in terms of the training. So by 2015, the error rates of the machines recognizing human faces were lower than the error rates of humans. Here's a way that a machine can reconstruct a picture. So you type in, this bird is red with a white and has a very short beak, and it gradually gets better and better at it until this is the picture it produces to correspond to that textual description. And this one's quite fun. You take a picture of some zebra and say, please color these like horses, and the machine turns them into horses. The top right-hand picture there is a series of entirely machine-constructed faces. None of those is a real face. They were all constructed by the machine. The machine was trained on Hollywood faces, so you may notice a bit of sort of Hollywood characterization in the faces as you look at them. Now, how do we apply this in the lab? Well, what we're wanting the machine to be able to do is to take very sparse data, a small number of measurements, and reconstruct what it thinks the full measurements would look like if it were to make them. So up there is a set of 64 pixels that have been measured on one of these stability diagrams. This is a single dot device. And now we say to the machine, now on the basis of the training that you've already received, what do you think the complete picture would look like? And to start with, when we did this, it only gave one possibility. We said, no, we want several possibilities. And so it produced several possibilities that were almost indistinguishable from each other. And for reasons that you'll see in a moment, we said to the machine, now don't be so sure of yourself. Make more allowance for the uncertainty in this. Let's have a bit more variation between the reconstructions. And so now the machine makes a slightly greater variation. Now, why is that important? Well, it's because we want to train it to get good at this. So we give it some training examples. They go into the encoder, and then they come out from the encoder, from the decoder, as some reconstructions. And the question is, how good are the reconstructions? And what we're trying to do is to train the machine to get better and better at making reconstructions that you can't distinguish from the original. So a way to think about this is an arms race between a forger and the police. So the forger is trying to forge driving licenses that the police can't detect to be forgeries. And the forger may get quite good at it, so then the policeman gets better and better at looking for the errors that there might be in a forgery, so the policeman gets better at detecting the forgeries. So then the forger has to work harder to make better and better forged driving licenses that the policeman is not able to detect. And that's the sort of process that we go through in training the machine for this deep generative model. And then, when it gets good at it, it can actually do sorting. So it can say, well, on the basis of these sparse data, I think it's this driving license or that driving license. And the way that it's doing it is that I showed you previously the different kind of reconstructions you can get, but they're not all equally probable. So one of the important things that the machine has to do is to do a probability distribution of the different candidate reconstructions and say which of them it thinks is more likely. So now let me show you how we might do this in practice. And the key to this is our information gain map. So what we're doing now is we're going to say, well, if I've got some sparse data, I can measure some more data. I don't want to measure too much. Which are the next data that will do me the most good in distinguishing between different candidate reconstructions? So this is what an information gain map looks like. Oh, sorry. This is some sparse data. So these are some data that have already been measured. And now what we do is we say, well, let's look at a particular scan, you know, across the data that have already been measured. And let's think what that would look like if we had the full information. So if we had the full information, the different reconstructions at x1 have widely differing values. Can I help? What are you after?
No worries.
All right. Do you want something? No. At x1, the different reconstructions have widely differing values, whereas at x2, they all have more or less the same value. So now you see the importance of when the machine makes the reconstructions of saying, don't be too sure of yourself, allow for some differences. And so if you say, where will we gain the most information by making another measurement? Well, if we make measurements at x2, we don't really learn very much, because all the reconstructions have more or less the same value there. So all we'll do is get that value, and it won't help us to distinguish between them. But if we measure at x1, the different reconstructions have significantly different values, and therefore when we get the actual measurement, that will help us to distinguish between the reconstructions that are plausible and the reconstructions that are less plausible. So what we now do is that we construct this information gain map, and the information gain map is really a way of saying, here we'll gain a great deal of information if we make a measurement, and there we won't gain so much. So where we have a high information gain value, it's strongly colored. Where we wouldn't learn very much, it's a pale color. So we can actually quantify that, and this is the measurement of the information gain. And really, this is just displaying what I've already said, that at x1, we'd gain a great deal from making a measurement there. x2, we'd learn rather less. So the process that we go through, and remember, this is on a machine that's already been trained with lots of data. And the training data that we use, some of it is real experiments. That's quite costly to acquire those data. Some of it is simulations. Those are cheap. Some of it is hybrid of the two. And what we do is we start off on the trained machine. We make a small number of measurements, 64 in that case. We generate a large number of reconstructions. I've shown 9, but there are actually about 100 reconstructions. On the basis of the differences between those reconstructions, the machine calculates the predicted information gain. It finds the maxima in the information gain map and makes the measurements there. That's what you see at the bottom. And then it iterates the process. So now it goes back and makes some new reconstructions in the light of the new improved data that it has. And then it makes a new information gain map, and so it goes on. So what I want to show you now is how that actually runs. And remember, what we're doing is the machine is running the experiment in real time. So these are experimental data that you're about to see. where the machine decides, on the basis of the information gain map, what the next measurement should be, and the experiment makes the measurement. It goes quite fast, so don't blink, but on the left-hand side are the measurements that have been made, and you'll see it starts off with 64 having been made. It calculates the acquisition map, which is a synonym for the information gain map. On the basis of that, more measurements are made, then a new acquisition map is calculated and it iterates around. And the thing to look out for is ask yourself, at what stage in this have I actually learned everything I'm ever going to learn from the experiment? And after that, the new data points are not really telling me very much at all. And you can imagine that because you know that this is going to be Coulomb diamonds, the middle bit of the Coulomb diamond where no current flows, you're not going to learn very much from that. So that'll probably be the last bit that the machine measures. The edges of the Coulomb diamonds are where all the information is, so those will be the places that it measures first. So watch this going in real time, and you sort of think, you know, at what point have I learned everything I'm ever going to learn? So can you see it running, and it's simultaneously updating the information, the acquisition map, and now it's just sort of filling in the blanks, and we're not really learning anything more because that's all white anyway. There's no current in the Coulomb diamonds if we neglect co-tunneling. Now let me give you another example of this, and this is an example where instead of showing the stability diagram as the source drain voltage and the gate voltage, I'm going to show it as two gate voltages. And this is really a prelude to how we do the tuning, because you'll see that in the top right-hand corner, lots of current flows and doesn't depend much on the electrodes. Bottom left-hand regions down there, nothing flows anyway, doesn't depend much. And the sort of sweet spot, well, already, I mean, isn't this amazing? Already on the basis of 64 measurements, the acquisition map is telling you where to measure next, because that's where you're going to gain the information. So let's watch that happening.
What model do you put in there? You put a model in there what you expect to see?
Pardon?
To calculate the acquisition map. You put the model in there what you expect to see? Or you have
we now are putting a model in some of our more recent results. These ones don't have any model at all. This one is just on the basis of training the deep networks. So the only model is the deep network model that the machine has developed itself in the latent space on the basis of the training it's received.
Oh, but you have trained it before?
Yeah, it was before you came in. We've trained it on data before, a mixture of experimental data and simulations, all right?
So basically you have trained it on what it's supposed to see.
What it expects to see, which is not the same as what it's supposed to see. All right, that's right. So it has been trained. So it's now learned quite a lot about these single dot devices. So in this case, it had already learned that probably in the top right-hand corner, even on those sparse 64 measurements, probably in the top right-hand corner, it's not going to learn very much. That's not very good. And the bottom left-hand region, there's no current at all, so that's not very good. So that's optimizing the measurement. Now I want to move on to the second topic of tuning the devices. And you'll see how the previous work leads on to that directly. Now there has been some automated tuning of quantum devices, and these have worked on manual input, they work on saved data, or they limit themselves to a very restricted portion of the parameter space. And what we're doing now is using much more powerful machine learning techniques than any of those published works or any others that I know of at the moment. If you know of better work, please say so, because we want to stay up to date. So you can think of machine learning as the science of uncertainty, or if you like, engineering good decisions in the context of uncertainty. And that's why the foundation of all machine learning is probability theory. That's why Gaussian processes are usually widely, because the Gaussian function is a mathematically well-behaved way of handling uncertainty. And a topic that is forging ahead and that we're making more and more use of is Bayesian probability theory. And you can think of Bayesian probability, or Bayesian optimization rather, like this. Supposing you have a belief, and the belief matters to you, but the belief is shrouded with uncertainty. And you want to reduce the uncertainty, and you're going to reduce the uncertainty by acquiring more data. But the data are costly to acquire, and therefore you want to choose very carefully what data you acquire in order to get the greatest cost effectiveness in updating the accuracy and the confidence of your belief in the light of the new data. And you can apply this to almost any walk of life. You could apply it to, the outcome of the next election here in Austria. You may have a belief about who you think is going to win the data, but the belief's not very sure. And so you want to get some more data to make your belief more accurate. You can do that with a public opinion survey, but public opinion surveys are costly. And therefore, you're going to choose your question and who you poll and all the other things that you try to optimize in order to get the best value for money out of your next opinion poll. And once you begin to see this process, you realize we all do it every day. I say something, Jörg's not quite sure whether I had a model or not in my thing, so he asks the question which will elicit an answer that will update the accuracy and the confidence in his belief. And you may know that Bayesian probability is not frequentist probability, which is what a lot of probability theory is about. It's, if I've got a probability here, it is the probability that belief A is true. Okay, that's what P of A means there. It's not frequentist. And the conditional probability is saying, if I get some new data B, what now is the probability that belief A is true in the light of the new data B that I've acquired? And you can see that schematically here. Let's suppose my belief is some function describing the behavior of a device, and let's suppose it's a function of only one parameter, just to make it easy to visualize. But the belief is shrouded with uncertainty, which is illustrated by the width of this mauve curve. And so what the machine does, if it's doing Bayesian optimization, is it calculates an acquisition function. And in this case, the calculation is that you'll learn the most if you make a measurement at this parameter here. So it makes a measurement at this parameter here, and then it updates the acquisition function in the light of that and says, well, now what will do you the most good is to make a measurement here. So now it makes a measurement here. So now we're trying to optimize the use that we make of the data to update the probability of the belief. That's sort of step one, and that's the kind of process that we were using for the automated decisions about what to measure next. Yeah.
Do you understand it correctly that the strategy to, let's say, take the next measurement is where the prediction has the highest uncertainty?
No, it's where it has the highest information gain, which might be close to where there's the highest uncertainty, but it's actually a separate thing. So you can think in terms of our previous pictures.
It's not plotted here.
No, the acquisition function isn't, but it will be on the next slide, all right? You could think in terms of our previous pictures, sort of, put very simply, you're going to have the maximum acquisition function at the edges of the Coulomb diamonds, because that's where the biggest uncertainty is. But actually, it's more sophisticated than that. And remember that our different reconstructions actually have different probabilistic weights to them. Okay, which is rather hard to display when you're doing this, but the computer's quite happy to work with those. So now the next thing we're trying to do is we're now actually trying to find, if we're doing Bayesian optimization, we might be trying to, it's what's technically called trying to optimize the objective. And in simple terms, you can think of this, that if we've got an objective which is measured by a score function, the pink curve in the top diagram, we're actually trying to find the maximum in the pink function. So now you can think that this is a bit more subtle than what we were doing before. So here's our acquisition function, which I've now plotted. In this example, the maximum in the acquisition function is here, so it makes the measurement there. But now it says, well, in the light of that new measurement, I've updated my belief about the pink curve. And remember, I'm trying to find the maximum in the pink curve. So now my acquisition function has got a peak here, okay? And the score function, if you like, we're going to make that the measure of how well we have tuned our device. So in tuning the device, we're trying to maximize that score function. So here's a way of looking at it in terms of the data you've already seen. So the gray contours are contours of constant score function. And we might be starting down here at the bottom left-hand bit of that yellow arrow. And what we're now asking the machine to seek to do is to find the peak in the mountain of the score function, because that's where the device is going to be optimally tuned. Now, I've displayed it in 2 dimensions there. Here it's displayed in 3 dimensions. If it's a single dot device, it's about 4 or 5 dimensions. We're going to come onto the double dot device where it's 8 dimensions, and that's even just for one device. And now the key thing that we have to do, and this is where a lot of work goes in, is to devise what should the score function be. And it turns out that for tuning up these devices, quite a good score function is a measure of how sharply peaked the, there's one, okay, did you see that one there? If you've got a nice sharply peaked curve of current against virtual gate voltage, that corresponds to a high score function. Don't worry, I'll show you some data like this again in a moment. But if you watch that movie running, the high score functions came when we had nice sharp peaks there, because that's what we've told the machine to look for. And it says virtual gate voltage, and the reason is because even in this display we've got 3 axes, but actually there are more than 3 axes. And so what we often try to do is to find this hypersurface. On one side of it, it's just completely conducting, so nothing much changes. And on the other side of which, it's not conducting at all, so nothing much changes. And the hypersurface is sort of dividing those 2 regions of everything conducting and nothing conducting, which is where the interesting results are. So you can watch the movie and you can see where the high score functions come, but here's just some stills taken from that movie. So this, in the experiment, was different samples being taken and displays of the core function. So here we've sort of got some peaks, you know, that's quite good. So we get a score function a little bit more than 1. And then on sample about number 20, we're beginning to get sharper peaks, so that corresponds to a higher score function. And then by the time we get over here, we're getting really these quite tight, narrow, nice, sharp peaks, which gives us a higher score function still. So now what we can do is we can let this loose on the data, and we can now extend it to, sorry, one of those got turned upside down, I apologize for that. We can now extend it to the tuning of double dot quantum devices. So up till now I've been showing you single dot devices, now double dot devices. So now remember that what we're looking for are those pairs of triangles, and whether the triangles form are a function of 8 different voltage parameters. So if we look at the, I'm sorry, the slides got corrupted. If we're looking around these regions in hyperspace, we can find some regions where you've just got stripes like that. That actually corresponds to it behaving like a single dot device that I was showing you earlier. It's another way of displaying the Coulomb blockade. But sometimes we can find the regions where we have these double triangles that indicate that it's going to work well as a singlet, triplet, qubit device. And you can see now what the different sections look like with the different score functions up here. Okay, so this got a score of 8.2, 8.3, 9.8, 10.6. Now, can you see why this one's got the highest score of all of them? It's because here we're beginning to see these double triangles. So now, and remember, the machine is finding these amongst vast spaces in many different dimensions. And to give you some idea for the parameters, the gate voltages typically can range from -2 volts to 0 volts. And typically within that range, about 1,000th, so about a 2 millivolt range, will correspond to something that's usable as a quantum device. And that's on one axis. And then there's 1,000th of that axis, and 1,000th of this axis, and now I've run out of ways of gesturing for the other 5 dimensions. So it's about 1/10 to the 24 of the available hyperspace of possible parameters that will actually give you the double dot behavior. Now you see why it's so hard to tune up. Now you see why it's so significant that the machine is good at it.
So basically, yes, you've got a sharp image in the last picture. Provides slight parameter fluctuations. What happens?
It's a crucial question. It deteriorates, Bill. It's an absolutely crucial question, and I can show you, I can illustrate that. Because what I now want to show is how we've now moved on to the next stage of reinforcement learning. So up till now, we've not been using reinforcement learning. One way that people became familiar with reinforcement learning was when Demis Hassabis, with his DeepMind thing, trained a machine to be able to do Atari games. All right, this was a particular game called Breakout. And did anybody ever play these games when they came out with Atari? Okay, and you have to move the paddle and try and score it. Now, what was amazing about this one was not just that the machine got very good at moving the paddle, but it discovered this incredibly clever strategy whereby if you can punch a hole in either side, then the ball can go like that at the back. And without any more movements of the paddle, you get lots and lots of score. So this was reinforcement learning. And what we're now doing is we're applying reinforcement learning to finding these very detailed spots. So now let me show you how that works. Okay, here is what the full data looked like. Okay, of course, we've got the full data, but the machine didn't. And here is the machine actually trying to find the place where it's nicely tuned up. Now, how is this working? Well, this was developed by Wu and Guyan, and it's deep reinforcement learning. What it does is it takes the total parameter space, and remember, I'm only displaying 2 dimensions of what's really an 8-dimensional space, and it chooses a region, shown here as a square, but really it's an 8-dimensional hypercube, and it makes a detailed measurement of that particular hypercube. And then what it does is the reward function is as if it's a child, where we say, well, if you get this right, you get a biscuit, you see. So the machine gets the equivalent of a biscuit if it gets it right. And it having measured one volume, it then gives a score to each of the surrounding pixels. And you can see that up there. You see, it might give it 0024. And it gives that score on the basis of its previous experience and training. So then what it does is it measures the next pixel and then repeats the exercise. And can you see up in the, it's just gone off the screen, but up in the top right-hand corner there, it actually had found a region of double triangles. So what this is now doing, this we use for the sort of second stage of fine-tuning. And it's very good at it. So now let me go, oh, well, you can watch it here, all right? Can you see this one? I think in this case, those are the final double triangles that it's trying to get to. Is it working towards those? Do you see it moving over there? I think this one may have got switched round. But here it is, in each case, working out. And there's only one thing you need to take away from this result, which is it doesn't need to measure the whole parameter space. Okay, it's measuring much less than all the parameter space in order, I think now you'll see that, do you see the double triangles that it's found? So it's found that with much more efficient measurement than simply measuring everything. So now, let me just move you on to the third method that we've got. And now this is a method that we use when that previous method has already found two triangles. But Bill, it's coming on to your questions, how stable is it? And how finely do you have to adjust everything else? So here's an example where it's found double triangles, but they're not absolutely brilliant double triangles. And so we want to make it better. And it's found those double triangles with those two gates, but there are some other gate voltages that it can tune. And so here it is, tuning those up and gradually finding a region where the double triangles are getting much, much better. And so the last slide of this lot is just showing you how it does that. And we're back to the deep neural networks now. So this diagram here, you can imagine, is one of the deep networks in our training system. So it's gone through the encoder, and it's not yet come back out through the decoder. And we have a way of measuring separation of points in that deep space. And basically, the bigger the separation, the worse the correspondence is to the ideal one that we've given it. So the target might be an ideal one. We've said, see how close you can get it to something like this, because this is really good for a double quantum dot device. And I mean, to put the numbers in, if it's a really bad fit, then there's a separation of about 12 units in this. If we feed it back the original one and tell it to match it up, it has a separation of about 4. And when it tunes it up, it gets a separation less than about 4.5. So this is a way now of doing the final fine-tuning. Just to, before I conclude, to pick up on your point, Bill, it's something we actually learned from these experiments, is that as you cycle the devices, so things do change. And one of the things that we've learned, and this was a scientific discovery, if you like, that came out of using this, is that the changes that happened were a rather monotonic change in the coupling of the gates to the device, and it was more or less the same for all the gates. So we tried to think, what could the physics of that be? And we think the physics is this, that as you have thermal cycling or other changes with time, the main change that's happening is the movement of trapped charges. And because these are band-gap engineered structures, if you move the charges around, you change the capacitance. It's the kind of thing that's measured in good old-fashioned CV measurements when you're trying to measure the dopant profiling of semiconductor materials. So we think that because you've got band-gap engineering, if you change the charge distribution, you change the edge of the depletion or accumulation region, which changes the capacitance, and therefore gives rise to this rather uniform change in the coupling of the electrodes to the quantum dot hole. We're still trying to work out the details of that, but we think that's what's happening. But certainly, these devices can change over time, I think primarily because of movement of trapped charges. So it's likely that in at least some of them, the tuning is not once for all, but it has to be constantly refreshed, like your sort of weekly update of your software. So let me just conclude and then just talk about some of the social implications. So I've told you about how we use the machine to measure, to decide what to measure next, and that's described in that top paper that's on the archive. It's about to come out in NJP Quantum Information. We'll have some PhD projects for anyone who wants to start, not this October, but October 2020. And we may next year, if grants come through, be in a position to advertise postdoctoral positions. But I just want to say that machine learning is an area in which you've got to engage in the social responsibility and the social issues. I was just reading on the plane yesterday, the 16th of September, that's next Monday, is it, issue of Time, and there's a whole piece there on the president of Microsoft, Brad Smith, and his public engagement on social responsibility of the industries that use machine learning, of which Microsoft is now the highest value because it's overtaken Amazon and Google and Apple and Facebook. But, you know, all of those companies and many others are harvesting your data. It's what Shoshana Zuboff calls surveillance capitalism. Every time you press a like button on Facebook, it's learning more about you. They now reckon if you've done 16 like buttons, Facebook has a better understanding of your preferences than your friends do. And by the time you've pressed 150 like buttons, it understands your preferences better than your spouse does. So all of these things have got big social implications. We had a story breaking last week in the UK of YouTube agreeing to pay $170 million fine in the US over children's privacy violation. It was harvesting data from children and using that to target advertisements on children. And of course, the targeting may not be restricted to advertising only. It may be also for other purposes that you might want to persuade people of. And it illustrates the kind of way in which many technologies, and particularly the digital technologies, are giving a new poignancy and a new accuracy to what's been around for a long time. A couple of weeks ago, I was speaking about this in India at a high school, and I was talking to the English teachers, and I said, what's your set text at the minute? What are you, the kids, reading? And their set text for this year is Shakespeare's play Othello. There's Othello and Desdemona. And how many people have read Othello, Shakespeare's play, or know of it? Okay. So what an incredible insight from 400 years ago of targeted persuasion based on fake news, all right? That's the dropped handkerchief and everything. That's what it's all about. So if you've got kids studying those kinds of texts in school, they've got a wonderful, wonderful opportunity to learn about how do you detect false information, how do you detect targeted persuasion, how do you ensure that you don't fall victim to it. In this particular case, 4 people lost their lives at the end of Othello because of Iago's targeted persuasion. And this is me and Andrew Steen, actually the person who invented one of the methods of fault-tolerant error correction, which is going to be crucial for quantum networks, and Hans Halvorsen, who's one of the most distinguished philosophers of physics in the US. He's at Princeton. And there we are talking about these issues. And after the photograph had been taken, Roger Wagner pointed out, if you look at the poses of the heads, they're rather similar to the poses of the heads on the title page of Galileo's Discourses, which I suppose would equate us with Aristotle, Ptolemy, and Copernicus, but any such coincidence is entirely unintentional. And that's just that in the book that we wrote together, It Keeps Me Seeking, we actually have quite a discussion in chapter 5 of some of these philosophical issues about machine learning. So this is just by way of emphasizing that we scientists, particularly those contributing to machine learning and using it, have got a wider social responsibility, and we need to accept that responsibility and exercise it. But in terms of the specific applications to devices for quantum networks, I've tried to show you how we use machine learning, first of all, to decide what the next measurement should be more efficiently than a human can do it, and then secondly, how we build on that to tune up quantum devices faster and more accurately than any human is able to. I think this is going to change the way that quantum networks are done. I think it's going to change the way quantum technologies are done. And I think before too long, you know, just as computers are already ubiquitous for experimental science, so machine learning will be.